Well, welcome to another RDWorks Learning Lab. Today we're going to push on with our quest for 1000 DPI. Now, you've heard me very cynically say that I don't think we're ever going to get there. Now, I thought with the work that I've already done, I may well have reached a boundary, and that boundary being 0.1 for certain and maybe 0.8 or 0.9 for a dot, possibly. We were basically bouncing off the wall of possibilities. As I was editing the video, something actually occurred to me. There was an elephant in the room that I wasn't noticing. Now, in the same way that this cup was bought for me by my stepdaughter, I think that this was a reject cup. First of all, it's pointing the wrong way, because the leg end is the other way. Now, the point I'm really making is it depends on how you read the information that's in front of you. There are many ways sometimes to read that information, and I think I missed a trick. Now, I haven't done this, haven't tried it, so we're going to have to go back to square one and take a look at it. Come in and I'll show you what I mean. When we look at this picture, we can see that there is a lot of aberration taking place. An aberration, if you remember, is that property of the lens caused by curvature and various other things that allows this beam here to focus at a different point to this beam here. So this beam focuses at that point, and this outer beam focuses at a slightly different point. Okay, so that's bad practice as far as lens theory is concerned. And it was one of the reasons why I did not use a meniscus lens in here, because a meniscus lens is designed to produce a much sharper focus point from a set of parallel rays. Now here on this second lens, you can see that the rays are not approaching the lens surface in a parallel manner. They're coming in at an angle. So therefore, all the properties that were designed into a meniscus lens have been basically destroyed, and we're not going to get an improvement of the focus point. I'm anticipating, and I haven't done this yet, but that's what I've got to go away and do. I'm anticipating that if I put a meniscus lens in here, I'm actually going to screw up the focus point worse than if I had a plano-convex lens in there. What am I getting at? Why would I want to put a meniscus lens in here to screw up the focal point? As I said to you, it depends on how you look at the information and what conclusions you draw from the possible implications of that information. Now, look, I've got the same picture here in a slightly exaggerated and cruder manner. I've got a beam coming in from the outside that crosses over the centre line and focuses with the beam that comes from the other side at point A. This second ray intersects the centre line here at a different point to beam A, and we produce a focus point B. And this third ray here, very close to the centre, goes all the way down here, and we get a focus point C. So we've got a whole range of focus points here caused by spherical aberration. And the whole aim of a meniscus lens is to reduce the difference between A and C. Now, I want to actually change that. I want to exaggerate the difference between A and C, because I believe that that may well give us something that we're seeking, which is a very high density small dot. Now, I've tried many ways to do this. Other people have suggested I should be putting the light through a filtering orifice. Well, we tried that before and it didn't seem to work. But, hang on, if I can make the spherical aberration worse, not better, I think I stand a fair chance of improving the quality of dot and the size of the dot. Now, how do I do that? Well, look, here's the power distribution in the beam. And the maximum power is happening around this area here. So effectively, we've got three different focus points for these three different rays. If you remember in the last session, I guessed at the focus point for my new compound lens to be between 5 and 6 millimeters. I was actually very happy to find that it was 6.5 millimeters. Okay, so it was bigger than I expected. And I didn't really think too much of it until I started thinking about this issue here. And then I thought to myself, well, that's surely because what's actually happening is we're getting maximum power at somewhere in this region here, not in this nominal region here. We're getting maximum power at a point in front where these central rays are crossing over. Not the average power, but this very specific high energy power. If we can exaggerate the difference between A and C, we will effectively be able to filter out all the low energy stuff from the outside and just work on a focus point which is looking at this high energy beam in the middle. And that's the principle of what I'm going to try and do today. I'm going to go away and design a slight variation of this lens system that I've got in here now to exploit the possible advantages of having a meniscus lens in there. Now, I know this whole process is going to be totally counterintuitive to optical engineers that are trying to strive for perfection. But hey, I'm looking at this problem on its head and saying, I think we might be able to exploit a natural property here to our advantage on the laser machine. Maybe, just maybe, this is the trick that Thunder Laser are using. I don't know, because we haven't had a chance to look at and examine and find out how they're doing it. We're second guessing and we're pathfinding for ourselves. Now, I'm not going to subject you guys to all the agony of watching me go through trying to find the focal distance for this particular lens and then the ideal power. Let's start off at this point here, 200 millimeters a second and 14% power, which was our reference standard that we had for this set of dots here. Now, they're not bad dots at all. There is a big problem here. Although they're 0.1 dots, more or less, there is a big difference in the colour between the dashes and the dots. And that is a warning sign that we haven't really got it right. We ideally want the dots and the dashes to be exactly the same colour. We're going to use the 200 millimeters a second and 14% power to try and find what the ideal focus point is for this new lens configuration, which is a 1.5 plano convex into a 2-inch meniscus lens. So here's our first attempt. We were expecting the focus to be longer than what it was before. In other words, we had 6.5 millimeters. So I've started this first test off at 5 millimeters. And look, it's absolutely rubbish. So then I jumped up to 7 millimeters. And well, if you look carefully, you can see that there are 3 lines there. The middle line has sort of got some dots on it. And you can see the dashes on the top line there. But you get a hell of a lot of burning to one side. Okay, so now we move on to 9 millimeters. We're nearly there by the look of it. Now, can we get it much better? So we go to 10 millimeters and it's getting worse. So let's drop back to this set of conditions here. And accidentally, I place the 2 dots almost on top of each other. The top set are 8.5 and the bottom set are 9 millimeters distant. So we work on from now 9 millimeters and we start playing with the power. Now we started off this set of dots here. They're very black. They're very good because look, the bottom set of dots are the same color as the dashes, which is absolutely a brilliant result. But we were running this at 200 millimeters a second and 14% power. Let's change it completely. And I went down to 100 millimeters a second and 13% power. They're not 0.1s because look, they're a bit dashy, but they're not bad. They're certainly all the same color. So that was at 9 millimeters. That was 9.5. Not very good. And just to prove the point, up to 10. Yeah, really rubbish. This time we went back to 9, but instead of 100 millimeters a second, I pushed it up to 150 millimeters a second, still 13% power. And for some reason or other, it actually makes it worse. I mean, the dots are joined up, as you may expect, but the thickness of the line seems to have increased as well, which is a little bit puzzling. So then we pushed on to 150 millimeters at 16%. We pushed the power up now. Not a lot different, considering we've pushed the power up quite a bit. And then we stayed with 150 millimeters a second, 16% power, and we've looked at 9 millimeters. That's 10 millimeters, so we're way out. And then we drop down to 8.5. Now this is still 16%, remember, so we're focusing back on the distance that we need to be away, and it looks as though 8.5, there's a huge difference between 9 and 8.5. So I started a whole series of results off again, and we're just going to quickly flip through these. The essence of it is there was 150 millimeters a second, 16% power. Now that's quite an increase in power, and we still have not got a thick line for 16% power. We've got a thin line because it's 150 millimeters a second, and speed normally makes the lines thinner and power normally makes the lines thicker. I experimented quite a bit here, and you're not interested in too much, but we went and pushed the power up to 25% here, and we still haven't pushed the line width up particularly. We've got a little bit of a halo around the edge of the line now, if you look, and around the edge of the dots, but they're certainly very crisp and dark, considering they are at 150 millimeters a second and 25% power, which is a huge change from what we have been using. We've been down at 14, 15, 13%. So we've come from 150 up to 200 millimeters a second now, still at 20%. Clean, sharp, crisp and thin. This is looking very promising. So now we're going to start working our way down the speed range and the power range, where we're at 100 millimeters a second and 15% power. Don't look particularly pretty, do they? As we're decreasing the speed and decreasing the power, things seem to be getting a bit worse. So we drop down to 112%. That's getting a little bit crisper. 111%. Wow, look at those. All the same colour. We're getting reasonable separation. I would say that they're almost 0.1 dots. Crisp, clean black 0.1 dots. And the dots on the centre line, by the way, should be the same size as the dots on the bottom line. And then we finally move on to this set of results here. What can I say? Pretty much the same colour. Not quite, but pretty much the same colour for dots and dashes. I could assess the average size of those dots as being about 0.7. And look at the colour between the dashes and the dots. Now this is at 100 millimeters a second and 11% power with a focal distance of 8.5. Everything is beginning to make sense now. We've got a longer focal distance. We've also got quite a wide range of power and speed that we can work over. I mean, we're getting reasonable dots there, very black and crisp at 100 millimeters a second and 15% power, as well as very nice dots at 100 millimeters a second and 10% power. So we've got a much larger variation in power that we can use now to play with. But I'm pretty confident, looking at the colour relativity between the dashes and the dots, that we're going to get some pretty interesting results out of this lens. And we've got to set it at 8.5 millimeters. Well, here's my first attempt using my standard Viamat card, which I class basically as grainless white wood, because basically it's pure wood chip. I have to say, I'm truly blown away with these results. I mean, I was blown away with them last time I got this far, but this is a smaller picture. Because the images are so much smaller, there are fewer dots per little item in there, so it should actually look a much cruder picture. Look at all these little gradations around here, and look at the quality of West and London. Staggering, isn't it? Well, that's because you're looking at an inkjet print. I'm actually playing with you at the moment, because I'm now going to do this. Unbelievable. Just so you can compare again. I mean, that's the size that I was doing it originally, and I've reduced it now by about 30%. And I've still managed to capture that detail perfectly. Let's take a look at the eye of the octopus in the original black and white print off of my inkjet printer. Look at the incredible amount of detail there is around the eye. We have the man in the sky, which always seems to disappear when I'm doing this. He's there absolutely perfectly on this one. Let's take a look at that very faint map in the background, should we? There it is there. And there it is there. I mean, it is a perfect sepia copy of this. Now, bearing in mind this is on card, there is not really just the merest hint of 3D-ness. When I say the merest hint, it's basically flat, but just in places where it's really black, there's just a hint of it being overburnt. And what resolution was this? This was done with Jarvis dithering, and it was done at 363 DPI, which was basically a 0.7 millimeter dot. I think we truly have now bounced off the edge of perfection. I mean, without burning the card to a frazzle, we've got a very, very wide range of colour there. But of course that colour is nothing to do with the burning. What we've got is a consistent colour dot and good gradation, grouping of the dots, that's giving us the impression of a grayscale picture. I mean, I'm just really am lost for words. I mean, I'm standing here with a smile that goes right round from my face to my bottom. Now, whether I should be able to achieve this on other materials is an interesting point, because this card, this white card that I've got here, is about the best possible material I think I can use. But hey, we ought to try this on some acrylic maybe, and then on some glass. Now, I can't emphasize this enough. The thing that I keep preaching is dot size, quality of dots. Once you've determined the dot size, you can determine the resolution of your picture. You can't get high resolution pictures from rubbish dots. Now, the dot size will vary depending on the ability of the material to accept the dot. So, although we've found that we can get 363 dot per inch picture out of a nice piece of white wood, basically, that white cardboard, this is cast acrylic, which will probably respond completely differently than extruded acrylic. From previous work, I know that this tends to come up whiter and give better quality dots than the extruded acrylic. So we're starting off with a piece of cast acrylic to see what we can achieve. Who knows? I'm expecting to get quite good results, but I don't know whether they'll be the same than what we've achieved with our white card. Maybe the focus will be different. It's a whole new world. I've got no idea, and so we shall have to experiment. We will start off the same as we did for the card, which is 8.5 millimeters, and don't waste your time trying to put a picture first. Always do your dot test first. If you can't succeed at the dot test, you'll be wasting valuable material trying to get a picture. You have to determine what your dot size is, your best dot size. Now, the other thing that's most important, you will need a flat surface to work on, and that flat surface must be true to the head, because this is probably fairly sensitive to within 0.5 millimeter. So you can't afford to work over a large area and have a 1 or 2 millimeter variation. So you've got to be pretty accurate with your table flatness relative to your head. Although it doesn't matter for testing, when you start producing a picture on thin material like this, the surface will tend to curl. So you need to clamp it down with magnets if you can, or stick it down with tape, or do something to keep it as flat as possible, because we've only got a very small variation in the depth tolerance of the focus. Now, I'm setting this up to 8.5 millimeters with my focus gauge, because that's where the previous best setting was. That might not be the best setting for this material. So, and the way that I do that is I make my head loose. Look, you can see that. So I'm lifting it up. I'm not leaning on the table. I'm lifting it up and just letting the weight of the head drop down, and then I'm tightening the head up so that I know that that is exactly what my gauge says, 8.5 millimeters. And we're using the speeds and feeds that we had before, which was 100 millimeters a second and 10% power. Right, don't look at the black marks behind, look at the white marks in front. The white marks are on the acrylic, the black marks behind are shadow. So ignore those, and that's our first set of marks done at the same settings as we did on paper, which is 100 millimeters a second and 10% power. Now, if I just shade out the light, you'll be able to see the marks a lot better. As you can see, we've got an inconsistent set of marks along the center of the top pattern. Now, that top pattern was done at 150 millimeters a second. The bottom pattern was done at 130 millimeters a second. So I think we've reached a pretty reasonable compromise where we've got dots that are, and the dots on here look a little bit bigger than they actually appear in reality. I think the dots in reality are again around about 0.08. So this should give similar results to what we were getting on the card. So let's go and give it a try. Now, I'm a total convert to Lightburn for this graphics work. It is literally a dream to use. I just click on here and I set my speeds and my powers exactly the same as I would normally. Now, because this is going to be used on acrylic, remember acrylic is a white printing, not a black printing. So therefore, everything that's black will come out white, and you have to remember to turn the negative image on. And here it is, just a switch which says negative image. And then we can change the dot here to 0.8, and it automatically chooses the resolution for us at 318 dots per inch. And I can select a particular type of dithering here, and the one that I've chosen for this is Jarvis. And that's it, that's all I have to do. I'm using no air assist, and there's a switch up there for air assist on or not. Okay. I can do a frame from here to check that the image is correct, and then I press the start button. But before I do that, what I have to remember is that this image, if you look at this image here, you'll see that it is the opposite way round to what you've seen the picture normally. And that's because when we view this picture, we're going to view it from the front. We're going to print it on the back and view it from the front. And printing on the back means that we're going to have to reverse the image. So all we've got up here is a little tool which basically says flip or flip. Now I'm afraid there is no hurrying this process. It's going to take probably best part of an hour. I think 50 minutes to print this picture. So we'll come back and look at it when it's finished. I didn't use air assist on this, and because the dots are so small and fine, basically we don't get a lot of this sticky debris that you normally get on acrylic. And all I need to do, to be honest, with a fairly, I mean this is a pretty soft brush, but any sort of soft or stiffish brush, you can brush the dust off the surface. Now this will not show up until we put something black behind the picture. And let's have a little bit of a closer look at some of the detail here. Now you can just about make out the West and London on that clock face, just about. It's not as good as the white wood one, but the octopus's eye and all the detail, that's pretty good. I mean, there's a phenomenal amount of detail in there that's so good. We've still got our map in the background, look. The thing that's missing this time really is up here in the clouds. It's not very clear, the face is not very clear. It's virtually not there. You can just about make out the end of his nose there, but it's pretty faint, and so that bit has failed. This acrylic version, superb as it is, and it is quite staggering, is not quite a full replication. Now I'm not sure that if I probably increase the power on the dots just a little bit, I might be able to pull these in. The information must be in the software because it's done it here. But I think overall you must agree that that is also absolutely mind-blowing, the fact that we can get that so good on a piece of acrylic. Now is 318 dots per inch 0.8 too ambitious? Well, one of the quick and easy ways to find out is to turn the job over and feel it. Is there any 3D-ness about it at all? That feels like almost a perfectly flat surface, which is really staggering. That means we haven't got any overburning there at all. We've got more or less the correct resolution for the dots. Next we're going to try it on a piece of glass. This is a material which lots of people are interested in, and again, don't attempt to do anything on here until you've run a test. We know what we started with for acrylic at a focus of 8.5. That may or may not be correct for glass. We shall have to find out. We go through the whole process of testing again. But we'll start off with 8.5 because we know that's approximately where the focal point is. But of course, with acrylic and paper, it's very soft. With glass, we're talking about it being very hard. But it hasn't got to burn into the glass. What it's got to do is chip the glass, like stone chips, with a little heat impact. So we've got it set to 130-10. Well, we've done some damage onto that glass, and it is very nice little dots. They're just about as good as they are in acrylic. Well, because this is a stone chip mechanism, the results are not as tight or as crisp as maybe they would be in a softer material. But I would say that we've got lovely consistent 0.1 dots there, which means we are limited to 254 dots per inch. That should be a pretty reasonable resolution. So we should be able to run Jarvis at 130 millimeters a second and 11% power. we'll let that cook for about half an hour and we'll see how it goes. Well, glass is a much more difficult material to work with, but normally with glass you tend to get sort of sharding, and I have to say that now that we've done this on here, there's absolutely no roughness or sharding at all, because we've obviously only done the merest amount of damage to the surface. I mean, the detail on the octopus and the eye, which is a really nice crisp part of the picture, looks pretty good. All this part down here looks good, except that we haven't quite got this detail here of West and London. But on balance, for engraving on a piece of glass, that is pretty good. Now I think that probably with a small amount of extra power in the dots, I might be able to get the man in the clouds without doing too much over burning or over damage to these pixels here. In other words, I just changed the power, not changed the resolution. So overall, I'm pretty pleased with my Mark II compound lens, and I think it proves the point that we can drive pixels a little bit finer than 0.1. I think we've now reached a new limit, which is 0.07 or 0.075 for certain materials. I mean, this has been done with a 0.1 resolution because I just can't get the dot small enough when I do the test pattern on it. So this has been done in accordance with the rules, and it's produced a pretty reasonable result. Well, here we are at a point where I think we should finish. I could do a lot more work with different materials, but I don't think I need to. The point has basically proven that yes, we can exploit some of the features that were not intended to be exploited with these lenses, and we can get some benefit from it. And I think I'm fairly happy that I've proved the point that we can use spherical aberration to our advantage by exaggerating it rather than getting rid of it. Now, I'm sure there are some optical engineers out there that will dispute what I'm saying. Do I worry? Look, I've got results. I don't need to worry about the theory. So I think this subject is basically now put to bed. I probably know as much as I want to know about photo engraving and getting the best dots possible. Unless, of course, there is another company in the world that can show me the way that I can get to 1,000 dots per inch. Thanks for your time, and I shall catch up with you on another session.